You know, usually when we think about what holds the human body together, we picture the solid stuff, right? Like bones, cartilage, tendons.
Right. The structural things.
Yeah,
It has a permanent address in your anatomy. It stays exactly where it grew.
exactly. But today we want to welcome you to a deep dive where we're unpacking the science, the history, and really the hidden complexities of blood.
Which is such a massive topic.
It really is. And I want to start by completely shattering a basic assumption you probably have about what is pumping through your veins right now.
The definition thing.
Yeah.
This always gets people.
Right, because when you look at the actual medical definition of blood, it is not merely a fluid. It's officially classified as a specialized connective tissue.
Which is, I mean, it's a categorization that throws almost everyone off the first time they encounter it in biology.
Yeah.
Because we instinctively associate connective tissue with, rigidity.
I was caught completely off guard by this. But my sources explain that histologists, so the people who study tissues, they don't classify things by how hard or soft they are.
No, they look at the origin.
Exactly, the embryonic origin of the cells. Blood cells develop from the exact same embryonic tissue, the mesenchyme, as your bone and your cartilage.
Yeah, and to take that a step further, the defining feature of any connective tissue is that it contains an extracellular matrix. So for bone, that matrix is calcified, right? It's hard.
Right.
But for blood, that matrix is liquid. It's the plasma. So calling blood a connective tissue is really the scientific community's way of saying that this substance is doing the structural work of transport, connection, and communication for your entire body, all at the exact same time.
That makes so much sense. If it comes from the same place as bone and acts as this ultimate connector, we can almost think of blood like a liquid skeleton.
Liquid skeleton, I like that.
It's this highly mobilized cellular soup that basically touches every other system you have. And today, we're going to explore how we went from ancient doctors thinking this liquid was like a consumable fuel to the modern marvels of hematology.
We've got a lot of ground to cover.
We do. We'll break down the microscopic components that keep you alive, look at some of history's most disastrous medical failures, and clear up those persistent misconceptions you probably picked up in high school.
It's a massive biological operation to unpack.
Yeah. And to ground us before we start, I just want you to sit with this number for a second. The average adult is carrying around 5 liters of blood. That's about 1.3 gallons.
It's heavy, too.
It is. It makes up 7 to 8% of your total body weight. That means your blood has a mass comparable to a major solid organ like your liver.
And it moves fast.
Right. That entire 5-liter volume completes a full circuit of your body roughly once every single minute when you're at rest.
It's just a relentless, closed-loop hydraulic system. But to understand what blood actually does, we really first need to look at what early doctors thought it did.
Because they were way off.
Oh, completely.
Yeah.
And that fundamental misunderstanding dictated centuries of incredibly dangerous medical treatments.
We have to talk about the humors, don't we?
We do. For over a millennium, the absolute, undisputed medical standard was classical humoral medicine. This was systematized by the Roman physician Galen of Pergamon back in the 2nd century CE.
Okay, so a very long time ago.
Right. And under this model, blood was one of 4 humors, alongside black bile, yellow bile, and phlegm.
And they didn't think it circulated at all, did they? Like, they had no concept of a loop.
Not in the way we understand it today. Galen basically taught that blood was produced in the liver from the food you ate, and then it was simply consumed by the body's tissues.
Just burned up.
Exactly. Like firewood burning in a fireplace. Wellness was entirely about the quantity and the balance of these 4 humors.
So if you had a fever or like inflammation, the logic was literally just, oh, you have too much blood, the fire's too hot.
Yeah, the internal logic was completely sound. If you accept the flawed premise. If illness is an excess of blood, then you must remove the excess fuel to lower the heat.
Which is why bloodletting became the standard therapy for nearly 2,000 years.
2,000 years of draining people's blood for almost any symptom.
But then William Harvey enters the chat, right? In 1628 with his treatise, De Motu Cordis. And what's wild to me is he didn't even use new microscopic technology to disprove Galen. He just used math.
Yeah, he used quantitative reasoning, which was totally revolutionary for medicine at the time. Harvey looked at the human heart, calculated its volumetric capacity, and figured out that the heart pumps far more blood in a single hour than the human body could possibly manufacture from digested food.
Or consume as fuel.
Right. It mathematically could not be a one-way street. Therefore, he proved, blood must circulate in a closed loop. He basically shifted the definition of blood from a humor to be balanced to a fluid to be circulated.
But I have to push back here a little bit. If humoral theory and bloodletting were the unquestioned standard for 1400 years, a math equation wouldn't just change everyone's mind overnight.
Oh, it definitely didn't.
I mean, doctors were essentially draining patients for every ailment under the sun. How did Harvey actually manage to convince anyone?
He had a really hard time doing it. The sources note that Harvey faced fierce resistance. He actually lost patients over it.
Really? Because they didn't believe him.
Yeah, they completely distrusted this new mechanical hydraulic theory. People are deeply attached to their paradigms. It took decades for the medical establishment to finally accept that Galen was wrong.
Wow. And I guess it wasn't really settled until the Dutch microscopists in the 1650s and 1670s.
Right, Jan Swammerdam and Anthony van Leeuwenhoek.
Yeah, they looked through early microscopes and literally saw red blood cells. That was the undeniable visual proof, right? Blood wasn't just a uniform liquid humor, it was particulate.
Exactly. It had distinct microscopic pieces. Harvey proved it was a circulating system, but it took the microscopists to show us what was actually doing the circulating in that closed loop.
And seeing those particles is really what bridges the gap to our modern understanding. Because if we strip away all the medical jargon, blood is really just doing 4 main jobs: transport, defense, regulation, and repair.
That's a great way to summarize it.
So if we start with the liquid itself, the plasma, that is the extracellular matrix we mentioned earlier.
Yeah, plasma makes up about 55% of your blood volume. And it is mostly water, about 92% water. But that remaining 8% is where all the biological magic happens.
Right.
You have hormones, nutrients, dissolved gases, and waste products like urea heading to the kidneys. But crucially, you have plasma proteins.
Like albumin.
Yes, albumin is fascinating.
Yeah.
Its main job is maintaining osmotic pressure. You can think of albumin as a biological sponge inside your vessels.
A sponge.
Yeah, it exerts a pull that keeps the water inside your bloodstream from just, leaking out into the surrounding tissues.
It is genuinely unsettling to realize that the structural integrity of our entire blood volume relies heavily on that one protein.
It is.
And when it goes wrong, you can literally see it happening to a person.
You really can. The liver manufactures albumin. So if a patient has liver disease and stops making it, or kidney disease and starts leaking it out in their urine, that osmotic pressure just drops.
The biological sponge is gone.
Exactly. The fluid escapes the vessels. That results in visible edemas, severe swelling, usually in the ankles or the abdomen. It's a direct, observable consequence of just this single plasma protein running low.
Okay, so floating in that finely tuned plasma highway is the primary cargo: red blood cells, the oxygen taxi service.
Yes.
We have roughly, 20 to 30 trillion of these in our bodies right now?
About that, yeah.
And to keep up with demand, the bone marrow is manufacturing about 2 million new ones every single second.
It's an astronomical production rate. And their entire existence is dedicated to carrying hemoglobin.
Right, the iron-containing protein.
Yeah, that binds to oxygen in your lungs and drops it off in your tissues.
But the evolutionary design of a mature red blood cell is what really caught my attention in the sources. Because to maximize the interior space for that hemoglobin, these cells physically eject their own nucleus.
They do. They ditch it.
They don't even have mitochondria, which are, the powerhouses of the cell. They run entirely on anaerobic glycolysis. I was reading this and thinking, they are like kamikaze delivery trucks.
That's exactly what they are.
They literally rip out their own engines and steering wheels just to fit more cargo in the back, knowing they're going to expire.
It is a remarkable evolutionary trade-off. They sacrifice longevity and self-repair just for sheer transport capacity. And because they lack mitochondria, they can't even consume the very oxygen they are carrying for their own energy.
That is so deeply ironic.
Right. After a lifespan of about 120 days, they just become fragile. And your spleen and liver quietly filter out and recycle around 200 billion of these expired delivery trucks every single day.
Okay, but if these red cells are just mindless delivery trucks that can't even repair themselves, they obviously can't defend themselves against pathogens. So who is handling security on this highway?
That falls to the white blood cells, the leukocytes. Unlike the red cells, which are all basically identical, white blood cells are a highly diverse population, even though they make up less than 1% of your total blood volume.
It's like an elite special forces unit where everyone has a different specialty.
Exactly. You have neutrophils, which are the most abundant first responders. They literally chase down and physically engulf bacteria.
You just swallow them whole?
Yep. Then you have lymphocytes, which include B cells that manufacture targeted antibodies, and T cells that hunt down virally infected cells. Then you have eosinophils, which specifically deploy to attack larger parasites or mediate allergic reactions.
So when you go to the doctor and they order a CBC, a complete blood count, it's basically a medical superpower.
It really is.
Because they aren't just looking at the total number of cells, they are reading the strategic deployment of your immune system.
Right. By looking at exactly which type of white blood cell is elevated, a doctor can often tell what is attacking your body before they even physically examine you.
That's amazing.
A spike in neutrophils strongly suggests a bacterial infection. Elevated lymphocytes. The body is likely fighting a virus. High eosinophils. That might point to a parasite or a severe allergy. It's a highly specific internal surveillance report.
Okay, so we have the plasma highway, the delivery trucks, the special forces. What happens if the highway itself breaks? Say you get a cut or an internal injury. That brings us to the repair crew.
The platelets.
Which, surprisingly, aren't even complete cells either, right?
No, they're not. They're tiny fragments. They pinch off from these massive cells in the bone marrow called megakaryocytes. And their entire job is hemostasis, stopping bleeding.
The mechanics of how they do this, the coagulation cascade, is incredibly intricate. When a vessel breaks, the platelets rush in. They actually change shape to become sticky and clumped together.
Yeah, they send out these chemical flares to attract more platelets.
But the real magic is the sequence of a dozen different clotting factors, numbered 1 through 13, acting like falling dominoes.
The end goal of those falling dominoes is to weave a durable protein mesh called fibrin. The platelets form the initial plug, but the fibrin weaves this physical net over the injury that catches passing red blood cells, reinforcing the site until it completely heals.
Which is brilliant.
It is, but the complexity of this cascade raises a really important point. Every single protein in that sequence is load-bearing.
Right, so if you remove just one domino, the whole cascade fails to reach the end.
That is the exact mechanism behind hemophilia.
Oh, wow, okay.
It's a genetic disease that became really famous because it ran through European royal bloodlines. Queen Victoria was a carrier, and it spread to the Russian, Spanish, and German royal families.
Just from one missing domino.
Exactly. It's caused by a missing or defective single clotting factor, often factor A through X. Because that one protein is missing, the dominoes stop falling, the fibrin net never forms, and the patient cannot finalize the clot.
When you realize how delicate that sequence is and how finely tuned the plasma and the cells are, the historical attempts to mess with blood blindly suddenly sound much more terrifying.
They were disastrous.
Which brings us to the most notorious failure of galenic bloodletting. December 14th, 1799. George Washington.
Right.
He fell ill with a severe throat infection, likely acute epiglottitis. And because humoral theory was still the prevailing mindset, his physicians treated him by draining his blood.
Over roughly 10 hours, they removed an estimated 5 to 9 pints of blood.
That is close to half of his entire blood volume.
Yeah, and he died that night.
I mean, obviously.
Right. Many modern medical historians believe that while the throat infection was incredibly serious, the massive bloodletting actively accelerated his death by inducing hypovolemic shock.
They bled out his transport system precisely when his body desperately needed those white blood cells to fight the infection.
It's the ultimate cautionary tale. You have this plausible-seeming theory, universally accepted, never tested against a control group, actively harming patients.
And early attempts at blood transfusions were just as reckless, right? I read that in 1667, a physician in Paris named Jean-Baptiste Denis actually transfused lamb's blood into a human patient.
Yeah, it was a deadly gamble.
Yeah.
Because they didn't understand microscopic compatibility, transfusions were essentially abandoned as too dangerous for centuries.
So what changed?
Carl Landsteiner in 1901. This is a clean case study in how one mechanistic discovery changes the entire world. Landsteiner, he was an Austrian physician. He was mixing serum and red cells from different colleagues in his lab.
Just experimenting.
Yeah. And he observed that some combinations were perfectly fine, but others violently clumped together, a process called agglutination.
How does that clumping actually happen?
Well, Landsteiner realized our red blood cells have different antigens on their surfaces. They're like tiny biological ID tags, and our plasma contains antibodies.
Oh.
If you introduce the wrong blood type, the antibodies in the recipient's plasma act like biological handcuffs. They latch onto the foreign antigens on the donor cells, linking them all together until they form a lethal microscopic traffic jam inside the veins.
Wow. And that discovery of the ABO blood group system earned him the 1930 Nobel Prize, didn't it?
It did, because it finally explained why some early transfusions were miraculous and others were fatal. He turned a dangerous folk remedy into a safe, routine, testable procedure. He also co-discovered the Rh factor later on with Alexander Wiener. That's the positive or negative part of your blood type.
Which actually leads to one of the most fascinating anomalies I saw in the sources, the golden blood rarity.
Oh, this is wild.
There is a blood type that lacks all 61 possible Rh antigens. It's nicknamed golden blood because it is a true universal donor for anyone with rare Rh-related blood types.
Yeah, it's incredibly pristine in that way.
But here is the terrifying catch. Fewer than 50 people on Earth have ever been confirmed to have it.
Right. And if they need a transfusion themselves, they can only receive Rh null blood.
Because their bodies have never seen any Rh antigens.
Exactly. Their immune system will form those biological handcuffs and reject absolutely anything else. It makes their blood incredibly valuable to medicine, but deeply dangerous for the individual possessing it.
It's a huge burden. There is one detail in the sources regarding older medical practices that genuinely confused me, though.
What's that?
Well, we just established how disastrous ancient bloodletting was, yet the notes explicitly state that medicinal leeches are FDA cleared today for use in modern hospitals. How is an ancient, debunked bloodletting tool approved by modern medicine?
I know, it sounds like a total contradiction.
Yeah.
But it is actually a brilliant evidence-based application of biology. They were FDA cleared in 2004 specifically for reattachment surgeries, like grafting a severed finger or an ear back onto a patient.
But what does a leech do that a modern surgeon can't?
Okay, so when a surgeon reattaches a digit, the tiny arteries that pump blood into the finger are relatively thick-walled, so they're easier to reconnect. But the microscopic veins that drain blood out are much thinner and harder to repair. They need time to regrow.
Oh, I see.
Right. If arterial blood pumps in but can't drain out, the tissue swells and dies. This is called venous congestion. So doctors apply a leech.
Because it acts like a biological vacuum pump.
Exactly. And furthermore, its saliva contains a powerful natural anticoagulant called hyaluron, which temporarily stops the coagulation cascade we talked about earlier. This keeps the blood flowing and relieves the congestion while the patient's own veins have time to heal.
That is incredible. So it's not about balancing humors at all. It's strictly about keeping the plumbing clear while the body repairs itself.
Exactly.
But, since the vast majority of our blood is hidden away doing all this complex work, it leaves a lot of room for misconceptions, and I'm going to fall on my sword here.
Oh.
For years, I firmly believed that the deoxygenated blood traveling through our veins was blue.
You are definitely not alone in that. It is arguably the most widespread misconception in human anatomy.
It's those high school biology textbooks. They always color the arteries bright red and the veins bright blue just to show the circuit.
They do it for visual contrast, right? But it creates this powerful myth. The truth is, human blood is always some shade of red. When it's fully oxygenated leaving your lungs, it's a bright, vibrant red. When it is deoxygenated returning in your veins, it's a darker maroon red.
Right.
The color fundamentally comes from the iron in the hemoglobin. When iron binds to oxygen, it changes shape and reflects red light.
So if the blood is always red, why do the veins in my wrists look blue or green?
It's basically an optical illusion caused by the physics of light scattering. Different wavelengths of light penetrate your skin and your subcutaneous fat differently. Red light penetrates deeply and gets absorbed by the dark blood, while blue light hits the surface layers and scatters back to your eye.
So the veins aren't blue.
The veins themselves aren't blue, the blood isn't blue. Your skin and fat are just acting like a blue filter.
I feel slightly better knowing it's a physics trick, although the sources do note that some animals actually have blue blood, right? Like horseshoe crabs and octopuses.
They do, but that is a completely different evolutionary path. Invertebrates, like horseshoe crabs, don't use iron-based hemoglobin. Their transport protein is hemocyanin, which uses copper instead of iron to carry oxygen. And when copper binds to oxygen, it actually turns a genuine blue.
That's wild. Okay, another thing. Because we can't observe our blood functioning, people seem incredibly eager to try and clean it. You constantly see targeted ads for juice cleanses or detox teas meant to, purify your blood. Is there any physiological reality to that industry?
None whatsoever.
Just completely fake.
Totally fake. Your blood doesn't need external detoxing from a commercial beverage. Your liver and your kidneys are already performing continuous, highly sophisticated filtration of your blood around the clock.
Yeah.
No juice is going to outperform an organ system that evolved over millions of years to do exactly that.
Save your money, folks. Let your organs do their job.
Absolutely.
Speaking of things that are more complex than they seem in advertisements, blood types. It's not just a simple letter grade like A, B, or O, is it?
No, we touched on this a bit with the Rh null anomaly, but ABO is just one single system. The International Society of Blood Transfusion recognizes over 40 distinct blood group systems.
40.
Over 40. The surface of a red blood cell is incredibly complex. It's studded with hundreds of different antigens. This is why matching blood for patients with rare types is such a massive global logistical challenge.
That is staggering. And finally, there is a tempting logic regarding red blood cells. If red blood cells are the oxygen delivery trucks, having more of them must give you more energy and make you healthier, right? Does that logic hold up?
It's a very dangerous assumption, actually. An abnormally elevated red blood cell count is a condition called polycythemia. If you pack too many physical cells into the liquid plasma, the blood literally thickens. It becomes highly viscous.
Like trying to pump a thick milkshake through a delicate straw instead of water.
That's a perfect analogy. And that severely raises the risk of life-threatening clots and strokes, because the heart has to work incredibly hard to push that sludge through your capillaries.
Oh, wow.
This is why blood doping in endurance sports, where athletes illegally boost their red cell count via transfusions or drugs like EPO, isn't just a matter of cheating. They're actively turning their plasma highway into a sludge, putting their cardiovascular system at massive risk.
So what does this all mean for you listening right now? Why does this deep dive matter? Because blood really sits at the absolute center of modern medicine. That routine, complete blood count we talked about, it can flag hidden infections, anemias, or even leukemias long before you actually feel sick.
It's our best diagnostic tool.
And the global blood donation system relies entirely on Landsteiner's century-old typing discovery to keep trauma centers running. I mean, a single car accident victim can need a dozen units. Pregnancy care relies heavily on Rh screening to prevent a mother's immune system from mistakenly attacking her own baby.
And the way we protect the global blood supply today, using advanced pathogen screening for HIV and hepatitis, is entirely built on our modern understanding of what blood is and how it functions as an interconnected transport network.
It is the ultimate internal defense and logistics system. But I want to leave you with a final thought to mull over, because this really stuck with me. We talked earlier about hematopoiesis, the bone marrow manufacturing 2 million new red blood cells every single second.
Yeah.
And we know those cells expire and are recycled after 120 days.
It is a system of constant, massive turnover.
Which means the blood circulating inside you right now is physically, materially, completely different from the blood you had last season.
Literally completely replaced.
Right. If this liquid connective tissue is constantly regenerating, you are essentially growing a brand new internal organ every few months. So if your liquid skeleton is constantly breaking itself down and rebuilding itself, what does that constant cellular regeneration mean for how we define our physical selves over a lifetime?
It's basically the biological version of the ship of Theseus. If every single part of the ship has been replaced over time, is it still the same ship?
Next time you look at a diagram of the human body, don't just focus on the solid bones holding you up. Think about the liquid skeleton rushing through you, breaking itself down and rebuilding itself 2 million cells a second.